In this session, we're going to explore basic functions. And if you downloaded that PDF from our website, then you should have a sheet with 10 sets of axes on them, which means we're going to look at 10 functions. What I would like you to do is go ahead and label them all as we go through them. So first, just underneath each set of axes, write down, say for the first two, constant and linear. And then for the next two, squaring and square root. You're going too fast. Pause the thing. And cubing, cube root. On the back side, you've got absolute value and greatest integer or floor function. And then finally, reciprocal and reciprocal square. Yes, I'll show you what they all look like. As a matter of fact, a constant function, as you know, is a horizontal line. And a linear function has usually has a slope and a y-intercept. Now, in this video, I want to show you how to write these functions down. And so a constant function, we're going to generally write them down or write it as f of x is equal to c. In this case, of course, c is equal to 3, and this should have arrows on both sides. And I typically will put arrows on my axes in the positive direction. The function definition for a generic linear function is f of x is equal to mx plus b. You're familiar with y equals mx plus b form. And your line should have arrows extending both directions. And in this case, your b is your y coordinate of your y-intercept. And of course, you have your rise and your run. And we can say that the slope is equal to the change in the y divided by the change in the x. That's not new. I'm just giving you a handle on this in function notation. Okay, on to the next. The squaring function is what we call a parabola. And I'll show you the square root function, and then we'll kind of analyze these a little bit. The square root function looks like half of a parabola on its side, and that's because it is. As far as the expression, the squaring function is f of x is equal to x squared, and the square root function, you've probably guessed, is f of x is equal to the square root of x. Let's see a little bit about why these have the shapes that they have. If we consider an xy table, inputs and outputs, for the squaring function, then I might consider putting numbers in like -3, -2, -1, 0, 1, 2, and 3. Squaring each of these in turn gives me 9, 4, 1, 0, 1, 4, 9. You can double check me on that if you like. And these correspond to dots like 0, 0, 1, 1, 2, 4, 3, 9. And of course we have corresponding dots to the left of the y-axis. That explains why it grows in the, kind of trends upward the way it does. That doesn't really explain what's going on with the gentle curve kind of in the middle. And I'm just going to blow this up a little bit so that you can see what I'm talking about. There's a nice gentle curve that defines a parabola. I've kind of lost it. That's what I'm talking about there. And this curve here is a very specific shape as part of a parabola. No other graph really has that same shape. And let me get this back to where it was, and we'll see why that, at least a little bit of why that is. Putting values in that are bigger than 1, say 2, 3, 4, we have outputs that are much bigger than the inputs, right? We square numbers and they tend to get bigger. Well, that's true for values that are bigger than 1, but for values that are less than 1, like a half or 1/4, when we square those, they become smaller, right? Like squaring 1/2 gives me 1/4. Squaring 1/4 gives me 1/16. Squaring 1/10 gives me 1/100th. In each of those cases, the output is smaller than the input, and what that causes is the function to kind of cling to the x-axis the closer we get to 0. And again, let me blow this up so you can see what I mean here. That's what's giving us this curve right here. Okay, I just point that out so that you know that it's not a sharp cusp. It's a nice gentle curve with the parabola. As far as the square root function, we can again consider x, y values, but notice that the domain of the square root function is numbers that are at least 0, right? 0 and bigger. So we can start with 0, 1. I could put 2 in there, but I'm not really going to want to deal with the square root of 2. If I needed to know the value, I could put it in the calculator and estimate the point plotted there. 4 is a perfect square, 9 is a perfect square. These seem to be good inputs for a square root function. Square rooting 0 gives me 0, 1 gives me 1, 4 gives me 2, 9 gives me 3, and that corresponds to roughly these dots here. It's a little bit hard to be perfect with the stylus, but you kind of get the idea there. And we again have this kind of graceful curve like we had with the parabola. It's kind of like, like I said, half a parabola on its side. Moving on, the cubing function and the cube root function look, they're a similar curve. In fact, their shapes are identical. They're just one is on its side. The expression for the cubing function is, of course, f of x is equal to x cubed, and that for the cube root function is f of x is equal to the cube root of x. And you should be writing these on your paper as you're drawing your graphs. And just like with the squaring function, we can consider the shape of the cube root function, the cubing function, from the xy table perspective. We can put values in like -2, -1, 0, 1, 2, 3 maybe. Cubing each of these, well, -2 cubed is -8. Then I get -1, 0, 1, 8, and then 27, which doesn't fit on my graph, but it's still there. And those correspond to these dots. Again, roughly, it's difficult to be exact with the stylus. And that gives us this shape here. And notice, again, in the middle, we have this kind of, it's different, but it's still kind of a graceful curve that flattens out near the origin. And that's because, for instance, cubing, say, 1/10 gives me 1,000, right? So as we get closer to the origin, the graph flattens out more. As far as the cube root function, we're going to have basically the same numbers, but they're going to switch places. The cube root of -8 is -2. The cube root of -1 is -1. 0 is 0. 1 is 1. The cube root of 8 is 2. And that's, of course, going to correspond to these dots here. And that indicates the basic shape of our graph. On to the next, the absolute value function and the greatest integer or floor function. The absolute value function looks like a V. The greatest integer function, we're going to talk about that a bit. Absolute value function, the description or the expression is simply f of x equals the absolute value of x. As far as the greatest integer function, there are a few different ways that I've seen this written. One of them is f of x is equal to, and then you use square brackets with a little vertical line inside of them, x. Or you might see f of x is equal to int x. That's just indicating it's the greatest integer. Or I've actually even seen f of x is equal to, looks like a little forward and backward L. That's kind of indicative of it being a floor function. And again, we'll explore that a little bit more in a minute. As far as the absolute value function, the output is the same as the input if the output is 0 or positive. So the absolute value of 0 is 0, 1 is 1, 2 is 2. And so to the right of the y-axis, this is basically the line y equals x. Oh, I forgot to, let me go back here. What I want you to do is in your cubing, in your cube root function, I want you to put arrows at the ends. Let's go back even further. In your squaring function, arrows on both ends. The square root function only gets an arrow as it goes off in the first quadrant. And that lack of an arrow at the origin indicates that that's basically the start of the graph. There's no more to the left or below that. Sorry about that. Back to where we were. We were talking about the absolute value function. If the input of an absolute value is negative, then what we do is we change the sign of that, right? So the absolute value of -2 is 2, of -3 is 3. And so to the left of the y-axis, we actually have the line y equals -x. So it could be stated that the absolute value of x is equal to x if x is at least 0, greater than or equal to 0, and it's equal to -x if x is negative, or if x is less than 0. We're going to deal with this kind of description of a function in a future video. Let's move on to the greatest integer function. The greatest integer function can be described as the greatest integer that is less than or equal to the input. So let's see what this means. X and y. Suppose we consider 2.1 or 2.5 or 2.9. The greatest integer less than or equal to 2.1 is 2. The greatest integer less than or equal to 2.5 is also 2. And the greatest integer less than or equal to 2.9 is 2. You see, we're not rounding off. We fall back to the next smallest integer. If my input is 2, the greatest integer less than or equal to 2 is actually 2. Not until I finally get to 3 can I say that the answer is 3. And then if the input is, say, 3.1, I'm also going to say the output is 3. And so that's why this is has the graph that it has with these horizontal little steps. In fact, sometimes this is called a step function. And a detail that's missing in the graph is that the left endpoints in each case should be closed dots, because those are where the function value actually exists, you know, as part of that line. So as to not violate the definition of a function, we can't have closed dots at both endpoints. Then the vertical line test would be violated. And as a matter of fact, we actually should have open circles on the right side of each of these little steps. So I've filled in all my circles and dots, and again, it's not evident in the graph, but between 0 and 1 the function value is actually 0. And it kind of seems like what we're doing is we're just taking the part of the number that comes before the decimal point, and that's true as long as the input is positive. But if we consider negative numbers, I'm going to do another XY table down here considering negative numbers, say -2.1, -2.5, -2.9, etc. The greatest integer that's smaller than or equal to -2.1 we might want to say is -2, but that's not true. If we consider a number line here, -1, -2, then the greatest integer smaller than or equal to -2.1 is -3. Same thing for -2.5, for -2.9, and so those are going to be the outputs for each of these numbers. And as we see up in the graph up here, if the input is -2 point something, then the output is way down here at -3. So for positive values, it's kind of like telling someone how old you are. You don't say, I'm 27.5 years old, usually, at least not at that age. You don't say, I'm 27.8 years old. You basically give the age that you turned at your last birthday. And so you just chop off the decimal value, the fractional value. But for negative numbers, you go for the last integer you pass. Say as you're getting larger and larger in value, the last integer you pass to get to 2.1 is negative 3. Because again, negative 2 is actually bigger than negative 2.1. Okay, I think I've drilled that to death. Let's move on to the last two. We've got the reciprocal function and the reciprocal square. The graphs of these are presented here. And as far as the expressions, the reciprocal function is f of x is equal to 1 over x, the reciprocal of x. For the reciprocal square, we have f of x is equal to 1 over x squared. The shapes look similar. A couple of distinctions, though. One of them is, for the reciprocal square, all of the output values are positive. None of them are negative. That's because of the squared. The other one is that the curves are slightly different, although it's not a distinction that I would expect you to be able to draw. You kind of almost need a machine to be able to indicate how the curves are different. But to understand these shapes, we can consider, well, XY table, as usual, and note that in each case, x can't be 0 because, 1 over x squared. We can't have a 0 in the denominator. We can, however, use values like a half, 1, 2, etc. And the reciprocal of 1/2 is, of course, 2. That of 1 is 1. And the reciprocal of 2 is 1/2. And so that corresponds to points like we have here, and gives us an indication as to why this shape is the way it is. If any of these values is negative, well, then its reciprocal is also negative, and so that indicates why we have the shape that we do to the left of the y-axis. As far as reciprocal square, take any input that you're allowed to take, not 0, take its reciprocal and then square the result. So 1/2, the reciprocal is 2, square that, you end up with 4. 1 will go to 1, of course, and then 2, take its reciprocal, I have 1/2, square that, I get 1/4. So that's why the dots are as I'm indicating here, and that gives us the shape that we have here for the reciprocal square. And if any of these inputs turned out to be negative, let's say, the outputs would be unaffected because, again, of the squared. So this is actually is just reflected to the left of the y-axis. Nope, just when I thought we were done. I forgot to put the arrows. Yeah, they're important to me. Arrows on the axes. Arrows to indicate that these curves go on forever in the trends that they are in. And those are our basic functions.